feature learning. Feature learning is a very important class of machine learning methods. Feature learning methods are very important because often we do not know what are the good features of a data point. So what I want you to learn today, or to recognize after today's lecture, that there are big challenges with using straightforward data as features. Remember, you could use for an image, you could use the red, green, blue intensities of each pixel as a feature. This sounds like a straightforward and a reasonable choice of features, but you get too many of those features. And there are other cases where when you take directly the raw data, or I call them raw features, so the raw features is in some sense the naive choice of features. I will discuss more about this in a second. And we have too many of these raw features. So we need to learn a few most relevant features. And this is actually provided by feature learning methods. So what feature learning methods do is they read in long raw data or raw feature vectors, like the red, green, blue values of an image or the image pixels, and output a typically very small number of new features, which are more relevant and kind of which have the information condensed in them. So the raw features, feature learning methods never add information, but they condense the information that is spread out over many raw features into a few most relevant features. So that's the basic idea of feature learning, which I will describe in more detail in a second. Then I will show you how to use feature learning methods to visualize data. One of the most popular ways to visualize data is to do a scatter plot, but a scatter plot typically takes place in a two-dimensional plane. So if you have more than two features of a data point, how do you represent those data? Well, you can use feature learning methods to learn two features and use these two features as coordinates in a scatter plot. Then we will talk about maybe the most important and most widely used feature learning method, which is called principal component analysis. This is a special case of feature learning methods when we constrain the extraction process to be linear. I will then tell you about another linear feature learning method, which is sometimes a very useful alternative, which is to use random projections. Okay, but first things first. So what are three components of machine learning? Yes. I want to see 10 answers. Yes, very good. Thank you. So data model loss. And maybe the most important thing or the most important component is data. So data points can be anything, any kind of object that has characteristics or properties, which we call features. So a data point could be a movie. And think about a high definition movie. When it's stored on some hard disk, it consists, or it's constituted by gigabytes of raw data. Think about the features, raw features of a movie being the red, green, blue value of each pixel in each frame of the entire movie. And then you easily get billions of features that describe one data point, which is some movie. But then how do we work with such high dimensional data? Ideally, I would like to understand the structure of a data set or a bunch of movies, for example, for recommendation systems. So if I want to choose a movie, I would like to start with a movie I know, but which I have seen tens of times, and then I would like to find out what are similar movies. So I would like to map those data points into a scatter plot where similar movies should be placed next to each other, and then I can navigate. So I can start with this movie, the campaign, and then see, okay, seems to be a similar movie. Let's see what this is, and so on and so forth. And feature learning methods can do this. So feature learning methods can create scatter plots of data points that are as high dimensional as all the pixels as obtained from all the pixels of a high definition movie. Yes, so this is one use case of feature learning methods, to represent them, to project them on a two-dimensional plane so that we can represent data points as dots in this scatter plot. So each data point is a movie, and we represent it by placing some marker at the location given by, or at the location whose coordinates are the first and the second feature. So one use for feature learning is data visualization, but there are much more kind of important reasons for doing feature learning. And I will now talk a bit about the curse of big data. There's blessing of big data. So we measure a lot of parameters or a lot of quantities about each individual of us. So we know almost up to the level of all the proteins of a human being. So we almost know all the molecules, or have an idea of the type of molecules in a person, and we can then use this information to tailor vaccines. So I heard about now new ideas for designing vaccines, personalized vaccines. So to this AstraZeneca or BioNTech Pfizer vaccines for COVID, which are tailored to you individually. And this is possible because we know so much about a person, for example, me, because every time we take a blood test, we get measurements, we can check the genetic properties of a person, and so on and so forth. So we know a lot, but there's also a curse with these tons of features. And simply speaking, it can overwhelm, it can kind of overly stuff the, or how should I say, it can confuse machine learning algorithms, which simply do not know on which features to focus or on which features to invest computational resources. So it's not trivial to find the most relevant information in billions of numbers, billions of numeric features. So we might easily waste computational resources on highly redundant or irrelevant features. And this one kind of symptom of this is overfitting. So a lot of features, using a lot of features might easily result in overfitting, which is not good, as we heard in a previous lecture. But also the computational requirements. When we use so many features, we have to work with feature vectors of length billion. And it's not easy to work with such large feature vectors in general. So to summarize, in using very large feature vectors or raw feature vectors, just by stacking all the measurements we have about a data point, like stacking all the red, green, blue values of a megapixel image results in a vector of length 1,000,000. But then typically when you use such long feature vectors, you might overfit. Remember in a previous lecture, I have explained or talked about the concept of an effective dimension of a hypothesis space. And if we use linear predictor maps, then the effective dimension is essentially the number of features. So typically this effective dimension increases with the number of features we use. And if we use 1 billion of raw features, then overfitting is likely unless we use at least billions of training data points or sample size. So overfitting typically kicks in as soon as this effective dimension of the hypothesis space is larger than the sample size, which is the number of training data points. And we rarely have billions of labeled data points. If you consider the design of a personalized vaccine, a labeled data point would mean to have a person being tested on a new vaccine candidate. And we don't have billions of such tests or trials, persons. So we need to somehow reduce the number of features. We need to break down the number of features or reduce the raw features to a small number of most relevant features. Yes. So after we apply feature learning methods, the number of resulting features is typically much smaller. And if the number of resulting features is smaller, then in general, also this effective dimension will be smaller. And so we avoid this overfitting threshold. So this overfitting threshold is when the effective dimension of the hypothesis space divided by the number of training data points or sample size is larger than 1. We need to avoid this. And one way is to push down the effective dimension by using less features. But which features? Well, feature learning methods automatically find out what are the most relevant features. Okay, so there's the statistical challenge, and there's also a computational challenge in using too many raw features, because already if you do linear regression, at some point you have to work with feature vectors, with the raw feature vectors. And if the raw feature vectors has billions of entries, then you have to work with vectors and matrices of whose size is around billions. And sometimes you might need to invert a matrix of this size, and inverting a matrix of size 1 billion is far from non-trivial. So then you might need some supercomputer, but you cannot do such computations or you cannot implement such machine learning methods anymore on your own laptop, for example. So there's also a computational challenge coming with using too many raw features. Okay, so this is the motivation why we need feature learning methods in general. And the basic idea of feature learning methods is rather simple. It's about learning maps. This is also what we did so far. So which maps did we learn up to now, or about which maps were we most interested so far in this course? What kind of maps? In which component of machine learning did we work with maps? In the model, because what is the model? How did I define the term model? It's a large set of different hypothesis maps. What is a hypothesis map? Well, a hypothesis map is nothing but a function that reads in a feature vector and outputs a prediction for the label, or a predicted label. And here we use something like a hypothesis map, but the output of this hypothesis map is not a predicted label, but it's a new feature vector. I call this X, the short feature vector. So we want to learn a map. I call this a compression map, W, that reads in the long raw feature vector with n being billions and outputs a new short feature vector with a small number n prime. So typically n prime is much, much smaller than n. So n might be billions and n prime might be 2 or 3. And the question is, how do we, again, it's very similar to the basic setup of machine learning. We want to find a map, but how do we know if a map is good at all? So we need some sort of a loss function to measure the quality of a map. And in feature learning, we use as a loss, we use the ability, or we use the best achievable recovery error or reconstruction error. So we take the output of this compression map and then use another tunable map to try to reconstruct the original raw feature vector as good as possible. And what we then want to do in feature learning, or what feature learning methods do, well, they optimize this reconstruction error. So feature learning methods tune this a compression map. So they search over, again, we search over a hypothesis space of different maps. But the map here is not used to make a prediction for a label, but it's used to output a short feature vector. And we want to find the particular compression map, W, that allows to reconstruct the original feature vector with a small, with a minimum reconstruction error. Are there any questions at this point? This is maybe the most important slide of today's lecture. This is the key principle underlying all feature learning methods. And there are some of them which I will talk about in a second. One is called principal component analysis. Another one is called deep autoencoder. All these methods rely on the same principle that is illustrated here in this slide. Yeah, it's not that difficult, the principle. So I understand that there are no questions at this point. Okay, so the next question then is how to make this into an algorithm. This seems a bit kind of vague here. So what could be a tunable map? What could we use here for tunable maps? Did you already hear about classes of maps that are somehow parameterized by a weight vector, for example? So do you know such tunable maps or spaces of tunable maps? Not a neural network, yes, exactly. An artificial neural network is nothing but a graphical representation of a set of different maps, and each particular map in that set is characterized by certain choices for the weights of this network. So neural networks, but that's already a bit more complicated tunable map. Could you think about more simpler tunable maps that we used so far in this course? So a set of tunable maps is nothing but a hypothesis space. So how many, which hypothesis spaces did you hear about in this course? Linear regression is a method that uses a very important hypothesis space. What hypothesis space is used in linear regression? What type of functions are used there? Linear maps, yes, that's what I wanted to hear. So another example for a tunable map is a linear map. A linear map, which takes in the feature vector, let's say C, and outputs weight 1 times raw feature 1 plus and so on and so forth, weight n times raw feature n. That's a tunable map. That's the set or the ensemble of all these maps obtained for different choices for the weights is called the linear hypothesis space, and this one is used by linear regression. Yeah, by the way, this hypothesis space is also used by other machine learning methods that we talked about so far. It's not only used by linear regression. Does anybody know another machine learning method that uses linear maps? Logistic regression, excellent. Yes, SVM, excellent. These are other methods that also use the linear hypothesis space. But how do these methods differ from linear regression then? How does logistic regression differ from linear regression? So they use the same model. So they must differ in one of the other components of machine learning. What are the other components? The loss function. Yes. Logistic regression uses the logistic loss, and linear regression uses the squared error loss. And the SVM uses the hinge loss. This is all detailed in chapter 3 of my book. Okay, so you already know some tunable maps. So let's look at the example, linear feature learning. So in linear feature learning, we use linear maps for the compression. So we use a linear map to transform or to map the raw feature vector into a short feature vector. And we also use a linear map for the reconstruction. So what we do in linear feature learning, and which is then what we see exactly what is called principal component analysis. We use a matrix. We can represent a linear map as a matrix. This is very nice about linear maps, and this allows us to use tools from linear algebra, which you are assumed to have learned last fall in the course matrix algebra. So we use a matrix for compression, and we use a matrix R for reconstruction. And linear feature learning is then about tuning these matrices. So tuning, trying out different choices for this compression matrix, and different choices for this reconstruction matrix so as to minimize this error. So we need to somehow measure this error. One option would be the squared Euclidean norm. Okay, that's linear feature learning. Another example, just we can also use another set of tunable maps. Let's use an artificial neural network. So the compression map is an artificial neural network. And this is a tunable map because we have these weights here. So each edge or link here is assigned a weight, and this we can tune. So we can change the values here such that the reconstruction error, again, is minimized. So instead of linear maps, here we tune nonlinear maps, which are represented by artificial neural networks. And this method is then what is known as an autoencoder or deep autoencoder if you use a special type of neural networks which has many such layers. So these neurons are organized in layers. But this is beyond the scope of this course. There are excellent courses at Aalto on deep learning, which discuss this in more detail. But the principle is exactly the same as for PCA. Tune the compression map such that you can reconstruct the original raw feature vector from the compressed feature vector as good as possible. That's the same principle of all feature learning methods. The difference then between these feature learning methods is which type of functions or which type of maps do you use for compression and for reconstruction, and which distance measure do you use to measure the error? Because you could, instead of the squared Euclidean norm, you could use here you could use another norm. Does anybody know another norm which we could use instead of the squared Euclidean norm? What other norm comes into your mind? We could use the one norm or Manhattan norm or whatever norm. And there are norms. So the study of norms, normed vector spaces, is a beautiful field of mathematics. And I'm not sure if this is covered in matrix algebra, but I'm sure there are excellent courses also at Aalto where you learn about the structure of normed spaces. So there are different options for norms here. Yes, I'm not sure. We don't require now details about normed vector spaces, but maybe you Google normed linear normed vector spaces, and then you will find most likely also a good course at Aalto. But I can dig that up if you write me an email and want to know more. Okay. Yes, so far we looked at feature learning in a completely unsupervised fashion. So we didn't use any labels. So just data points are characterized by long raw feature vectors, like the red, green, blue values of a pixel, but we didn't care about the label of an image, let's say, if the image shows a cat or not. Was not relevant up till now. So up till now, we just talked about plain feature learning methods, which just compress the raw features into a smaller set of new features that allow to reconstruct the original features. So this is, in some sense, this is nothing but a compression, like zip. No, it's not zip, because zip is lossless. And here we typically have a non-zero reconstruction error. So this is a lossy compression of the original raw data or raw feature. But if we look at feature learning in the context of a machine learning problem, then what we are mainly interested in is not that the learned features allow us to reconstruct the raw image or the raw pixels, but we would like these features to be most useful for predicting some label. So we would like to learn features that are not necessarily good in allowing to reconstruct the raw features, but which are very good and very relevant for predicting a label. And this we can take into account also in feature learning methods just by using a different loss function or a different error. So instead of using this reconstruction error, we could use like the resulting accuracy, prediction accuracy, or 0-1 loss on a training set when we use binary labels. So we can take into account label information very easily here in this setup of feature learning by using a different error or loss criterion. So instead of a reconstruction error, we consider the ability of this short feature vectors to be used for accurate prediction of a label. Okay. Yes. And then what is also nice about this setup for feature learning, we can bring in also privacy preservation. In many machine learning applications, we shouldn't, or we are not allowed to touch, to share parts of the data, like the name or the identity of persons for which we look at the healthcare records, but we would like to make a diagnosis for a person. And for this, we might not really need the name of a person or like the gender of a person, but just some measurements. And instead of manually selecting privacy preserving features, we can learn privacy preserving features. And we can learn such privacy preserving features by requiring that it's not by requiring the short feature vector to not allow by any method to predict some private information. So let's say we want to know the food preference of a person. So the label, the quantity of interest of a person is a data point, is the food preference. Does a person like apples or does a person like pizza? This is what we are interested in. And we would like to find which features of a person are relevant for predicting if he or she likes pizza or apple. For example, is a relevant feature of a person if he is from Austria? Does this feature of a person help us to predict if the person likes pizza or likes more apple? But then on the other hand, we would like to avoid, we do not want to use any sensitive information like the gender of the person. And there are feature learning methods which exactly do this. So they find out what kind of insensitive information about a person, like the height or the weight, allows to predict the label, but does not allow to predict the gender. Okay, so the height and the weight might be actually might be not good in this case, because they might be provide information to predict the gender. But there might be other features that can be learned for only predicting the food preference, but not allowing to predict the gender or the name of a person, the identity. Okay, so I will now go a bit more into detail for the linear feature learning methods. And the optimal linear feature learning methods is called principal component analysis. So remember, in linear feature learning, we constrain the compression map that takes the long raw feature vector C and maps it into a short vector of most relevant features X. And we also require that the reconstruction of the original raw feature vector, so this is the reconstructed version of the raw feature vector, and this is typically different from each other. In general, we will not be able to perfectly reconstruct the long raw feature vector. So there will be some error. And what linear feature learning methods do, in particular PCA, they choose, they find or compute the compression matrix W and reconstruction matrix R, such that this error here, measured in the squared Euclidean norm, is minimum. And we can interpret them also, so we can interpret this PCA, principal component analysis, again as an instance of empirical risk minimization. And what PCA does, it minimizes the reconstruction error. So this is the reconstruction error for the ith data point. So this here W applied to the raw feature vector of the ith data point is the short feature vector for the ith data point. And then we apply the reconstruction matrix. So this whole thing here is the reconstructed raw feature vector of the ith data point. So this is Z hat I. This is the reconstructed raw feature vector. And this is typically different from the original raw feature vector. So there will be an error. And what PCA does, it tunes or chooses or learns the compression matrix W and reconstruction matrix R to make this average reconstruction error as small as possible. Yeah, so PCA is obtained as the solution of an optimization problem. In particular, the optimization problem is to minimize the reconstruction error. Yes, and what is nice about principal component analysis, or what is nice about this problem, it can be solved in closed form. So you can find out precisely what is the optimal compression matrix W. There is no approximation involved. You can really find the optimal compression matrix W. And this optimal compression matrix is built by eigenvectors, particular eigenvectors of what I call the sample covariance matrix. So this here is the sample covariance matrix. And it's obtained by computing these products here, or outer product. So this is sometimes called an outer product. But you don't need to remember that in detail. So this is sometimes called an outer product of the ith raw feature vector, and we sum those outer products over all data points. And the average of these outer products is what I call a sample covariance matrix. And what we then do is we compute an eigenvalue decomposition of this sample covariance matrix. As it turns out, this sample covariance matrix has very nice properties. In particular, it's always a positive semi-definite matrix. And a positive semi-definite matrix is like, these are the nice matrices, so to say. So the life is easy when working with positive semi-definite matrices in some sense. One example, or one indicator of the nice behavior of PSD matrices is that they allow for an eigenvalue decomposition with orthonormal eigenvectors. So these eigenvectors here, U1 up till UN, they are orthonormal. So it's nice to work with them because they are orthogonal, so they don't influence each other that much in some sense. So they are orthonormal. And also the eigenvalues are real valued and non-negative. So we typically like to order them in a non-increasing order. So lambda 1 is the largest one, then we have the second largest one, and then we have the smallest one, lambda n. Some of them might be equal. So there might be some which are actually have the same value, but we still can find different orthonormal eigen vectors to them. So this here is maybe the most mathematically involved part from my lectures. And we don't expect you that you understand all the details about this. You do not need to understand eigenvalue decompositions for the quiz, just as a heads up. Okay. So that's pretty cool because how many of you know how to compute an eigenvalue decomposition? Using some programming language. Well, I can tell you it's one line of Python code, of course, but there are many libraries which provide this functionality. So you input the sample covariance matrix, and they return, these methods return the list of eigenvectors and the eigenvalues. This is really, there's 50 or I would say 100 years of brain power put into efficient algorithms for computing this eigenvalue decomposition. This is already a technology. This is highly developed tools, or there are highly developed tools for implementing this eigenvalue decomposition. And this is what is so nice about linear feature learning, because in the end, it boils down to computing an eigenvalue decomposition. Here's one question: what are the top eigenvectors? The top eigenvectors are those which correspond to the largest eigenvalues. So the top eigenvector is an eigenvector whose corresponding eigenvalue is the largest. So yes, and now the big result is, or the very cool result is, the optimal compression matrix the rows of the optimal compression matrix are just the top eigenvectors of this sample covariance matrix. So here I forgot something. This is not correct. Here we need to transpose, I think. Yes, we need to transpose it. So we can build the optimal compression matrix. Let's say we want to know n prime equal 2 features, because having 2 features is good to represent data points in a scatter plot. So if we want to find the best compression matrix for n prime equal 2, we just compute the eigenvalue decomposition of the sample covariance matrix and then pick the first 2 eigenvectors, stack them in the matrix, transpose it, and apply it to the raw feature vector. Okay. So here's an illustration of the resulting entry vectors of these eigenvectors of the sample covariance matrix. So if we look at the data set here, each blue dot here represents 1 data point. Then it turns out that the eigenvectors of this of the resulting sample covariance matrix are aligned or oriented approximately like this. So there's one direction. So this first eigenvector, this is the top eigenvector. The top eigenvector of the sample covariance matrix. And this top eigenvector is in the direction of the maximum of the maximal variation. So the data points vary or spread out the most in this direction. And the second eigenvector is then the direction in which they spread the least. So intuitively, the first eigenvector, or the kind of the first feature that you get from PCA, the top feature, when you say n prime equal 1, PCA gives you 1 feature. And this feature is nothing but the projection or component of a data point, or the raw feature vector on this direction of maximum spread. So this would be then, so if this is let's say C1, then you project this on this line here, on this direction of maximum variance, and you get the short feature vector for this data point x1. And let's say this here would be C2, the second data point. And you get the feature for this by projecting again on this direction of maximum spread. So the output of PCA is then the coordinate or the component of each raw feature vector along this direction of maximum spread. Okay. Yeah. Although it seems so nice and easy, PCA is typically computationally challenging. Why do you think? Do we need still quite a lot of computation for PCA? Well, if we implement it according to this slide here, using an eigenvalue decomposition, we have to do an eigenvalue decomposition of an n by n matrix. And if n, the number of raw features, is billions, then we have to compute an eigenvalue decomposition of billions, of size billion times billion, which is too much. And therefore, there are variants of PCA which try to avoid this computational burden of computing a full eigenvalue decomposition, because what we need in the end is not the full eigenvalue decomposition, but we only need the first n prime eigenvectors. So there are methods that kind of more economically do this eigenvalue decomposition, in the sense they only compute the first n prime eigenvectors and not all n eigenvectors, and they significantly save computational complexity. Okay. Then the question, of course, is also how to choose this n prime. So far, this n prime was given. So we wanted, we looked at linear feature learning methods that take the raw feature vector of length n and optimally compress it into a short feature vector of length n prime. And this n prime was given. This was a given parameter. But in practice, nobody tells you, your customer doesn't tell you what a good n prime is. So you must find out a good n prime. So yeah, there's a very good comment on the chat. The maximum possible choice for n prime, or useful choice, is of course n, because if we allow the shorter feature vector to be on the same length as n, then of course we can find a good representation by using just here the identity map. So by using as the short feature vector the raw feature vector of length n, because this feature vector allows to perfectly reconstruct the original feature vector. So this is then trivial. Trivial if n prime would be n, but typically we want n prime to be much, much smaller than n. Okay, so how can we choose n prime? Well, we could look at how the reconstruction error, the optimal reconstruction error, depends on n prime. So we could say we use some n prime, like n prime equal 2, and then find the best compression matrix and the best reconstruction matrix, and then look at what is the reconstruction error we get from this optimal compression and reconstruction. And what we get then is a plot that shows this optimal reconstruction error as a function of the number of new features. So this here, this n prime, is the number of new features that we want to extract from the raw feature vector. And we see here, so there's one special point. If n prime, the length of the feature vector that we want to have, if this is allowed to be equal to n, then we obtain reconstruction error 0 trivially, because we just use the original raw feature vector as the short feature vector. So here we can say x equal z. So we just copy the raw feature vector as the learned feature vector. But in general, we cannot do this, because in general we require the length of the short feature vector to be much, much smaller than the length of the raw feature vector. And then we just cannot copy it because the length of those vectors is not compatible. So we typically will then also get a reconstruction error, non-zero reconstruction error, which will decrease. The more components or the more features we want to learn, the more information it contains about the raw feature vector, and so the smaller we can make the reconstruction error. And sometimes we might be lucky and this dependence will look like this. So there will be a steep decrease in the beginning, but then it will flatten out. And then we might choose this number of features in this kind of knee or elbow, after which this decrease becomes smaller. So even if we use more learned features, we cannot reduce the reconstruction error significantly more. So this might be a useful strategy for choosing the number of features. However, in some applications, n prime is given. If you want to represent data in a scatter plot, which has 2 dimensions, well, you need to choose PCA with n prime equal 2. Okay, then I quickly mention variations of PCA, of this original PCA. So one variation is called robust PCA, which can handle outliers. So if we would have a single data point that is completely off the bulk of the data points, then we would like that this outlier has almost no influence on the learned compression matrix. And does anyone have an idea how we could cope with outliers? The problem with outliers is that if we learn a compression matrix, we want to make the reconstruction error as small as possible. And if we use the squared Euclidean norm as the reconstruction measure, then having such a large reconstruction error is amplified by squaring it. So how can we reduce this effect of a single large reconstruction error? So when we have an outlier, then one term here, so for this sum here for the reconstruction error, goes over all data points. And for one component of this sum, which corresponds to the outlier, this squared Euclidean norm will explode because we square the norm. So how could we avoid this? Does anyone have an idea or a guess how to make this more robust? Well, we could choose a different norm, or instead of the squared Euclidean norm, just use the Euclidean norm. Or use the one norm. So robust PCA methods are obtained by using different norms here. The standard PCA is using the squared Euclidean norm. But we can obtain robust PCA methods by using a different norm here, or using not the squared norm. Yes, you could also use square root, but I'm not sure if there's a method using this. I'm not sure what be the challenges, but could be possible, yes. The norm is a design choice, or the error measure in general. Doesn't need to be a norm after all. Okay. So then we have robust PCA, which are more robust to outliers. So having a few outliers in your data point doesn't screw up the whole feature learning method. Then another variant is based on a probabilistic model. In particular, probabilistic PCA is based on representing these data points as realizations of a Gaussian random vector. And this is similar to what we heard about in soft clustering, where we used a mixture of Gaussians. But here it's even simpler. Here we only use one Gaussian distribution and interpret all the data points as realizations of this Gaussian random vector. Okay. Yes. Yes, I also mentioned sparse PCA, and in sparse PCA we constrain this tunable map here to only take into account few raw features. So we want each new feature to depend only on few raw features. And this might be useful in some applications. This is called sparse PCA, but I will not go into more detail here. I just want to highlight one important use case of PCA is to bring down the number of features, because a large number of raw features bears the risk of overfitting. So we would like to learn a few relevant features and then use these relevant features, few features X, as the input for a classification like logistic loss or regression problem. So one use case of PCA is preprocessing to construct the feature vectors for a machine learning method. So far in the course, we assumed the features are given. Somebody gave us features of a data point, but we could use PCA to learn good features. However, there is one pitfall here in this approach, which might be very relevant in practice, because PCA ignores the label information. So I want to illustrate this here by this simple data set. So let's say we have data points represented by two raw features. So we have raw feature C1, which is represented here on the horizontal axis, and we have raw feature C2, which is represented on the vertical axis. And each data point is characterized by a label, which is either a triangle or a circle. And now we would like to learn a single feature. Let's say for some reason we don't want to have two features for a data point. We want each data point to be characterized by one and only one feature. So what could we do? Well, we could use PCA to learn a single feature using the top eigenvector of the sample covariance matrix. However, the sample covariance matrix doesn't care at all, and PCA in turn doesn't care at all or ignores the labels. So it looks at each data point equally, and it computes the sample covariance matrix, and the top eigenvector is in the direction of the maximum spread of the data set, which is this here. And if we project these data points on this axis, we obtain these features. And you see that, for example, this data point, the feature for this data point almost lies on top of the feature for this data point from a different label. So we obtain features which lie on top of each other, and we cannot really distinguish between the different labels in using the new features. So PCA learns the completely wrong or very bad direction or bad feature for classifying data points. PCA learns features that are good in allowing to reconstruct the original data point. So to tell us in where the data point was on that direction, but it doesn't allow us to reconstruct on which position it was in that direction. But this direction is actually the relevant one. This direction is irrelevant for the classification, because in this direction the class labels are, or the data point labels are all the same. So this direction is useless for classification purposes. This direction is the important one for classification. But this is ignored, or this is not delivered by PCA. And that's why we typically use a simple adaptation of PCA, which basically uses a different error criterion. So instead of a reconstruction error, we use linear compression with a reconstruction performance measured by the ability to predict how well can we predict the label. And one very simple such method is called Fisher's discriminant analysis. And the idea is quite simple. So we try out different compression matrices. So if we use only one feature, X, one learned feature, then the compression matrix reduces to a single vector, row vector. So what we like to do in Fisher's linear discriminant analysis, we want to learn a compression such that in this new feature space, using a single feature, the class means, so we can compute for each class. So for this triangle class, we can compute the mean feature. So this would be the mean feature for the triangle class. And here we compute the mean feature vector, or mean feature for the circle class. And what we do in Fisher's discriminant analysis method is we choose, so we tune this weight or this direction, which kind of decides how these data points are projected into this one-dimensional space. And we choose this projection such that the difference between these means is maximized, or the distance between these means is maximized, because intuitively, and one can make this also more precise, this distance between this class means is what determines the ability to predict the class label, or to predict the label from this single feature. Okay. Yeah, and then finally, just quickly mention one alternative to PCA. So PCA is the optimal linear compression matrix, or linear compression method, linear feature learning method. A challenge of PCA is that it requires to compute eigenvectors of a sample covariance matrix. And this might be a very large matrix, so computing these eigenvectors might be computationally challenging. And then there's a very cheap, a computationally cheap alternative, which is just use a random matrix, or I call it a random projection. Just generate this compression matrix W by drawing random numbers from a random generator, independent and identically distributed, for example. So there's no learning or tuning, there is no eigenvalue decomposition involved. You need just run some random number generator several times. And it turns out that using this completely random compression matrix delivers new features which allow to solve machine learning tasks like predict the label almost as good as using the original feature, long raw feature vector. And this is known, so this is one of the key ideas of a field called compressed sensing. So just randomly project or randomly map the long raw feature vector into a small set of new features, and these randomly obtained features are almost as informative as the billions of raw features. Yeah, so here we use the same random matrix for all data points. So we once generate this matrix W, and then it's fixed. So for all data points that come in, we use the same matrix W then. But in the beginning, we generated completely randomly. And in particular, there is no sample covariance matrix needed and no eigenvalue decomposition. Okay, so to wrap up today's lecture, feature learning methods automatically determine most relevant features. So ideally, we stuff in billions of raw features, and these methods spot the most relevant quantities or combinations of these raw features. For example, if we only learn 2 features, we can represent data points conveniently as a scatter plot in the plane. Then I have discussed in some detail the optimal linear feature learning method, which is called PCA, Principal Component Analysis. This PCA constrains the compression map, which takes the raw features to the new feature vector, to be linear. So we can represent it by a matrix. If we allow for nonlinear maps, like obtained from artificial neural networks, we obtain different feature learning methods. Then I have highlighted that PCA per se ignores label information. So it might be not very useful in using straightforward or naively using PCA in as a pre-processing step for a regression or classification task, because PCA learns features that are most useful for reconstructing original data points, but might be not so useful for the actual final goal of the machine learning method, which might not be compressing data points, but which might be to predict the label. And for this, you might need to adapt the error criterion of PCA. Okay, and then finally, I have mentioned random projections or random compression matrices as an alternative, which is computationally very light or cheap, and might in some settings achieve a competitive performance similar to learned feature learning methods like PCA. Okay, are there any questions? So here's one: how many raw features should be applied? Should be to apply these random projections. So there are theoretic results that tell how well these random projections are doing, depending on the size depending on the size of the raw feature vector. So typically the number of learned features, or the optimal choice for the number of learned features, depends on the length of the raw features. Then another question: when will quiz 6 for round 6 be opened? Yeah, as I mentioned before, I do my best to open it as soon as possible, but the latest next Monday. Then another question: why randomly choosing projections will work? Any theory? Yes, so the theory behind this is called compressed sensing. I suggest you Google compressed sensing and start to read, for example, start from Wikipedia and try to find the first papers from, I guess, 2006. Around 2006, this took off, where it was shown that using this these random matrices allows to speed up medical imaging tasks. So where data points are X-ray scans, and using these X-ray scans in its raw form, like pixel intensity or grayscale values, was so slow that, for example, you need the patient to be fixed for a long time. And using compressed sensing, it was possible to speed up this process significantly. And I heard that in some cases, this really means saving lives or not. Okay. Then is MCA usable for discrete features, or PCA? I guess PCA is meant. Yeah, there are variants. There are variations of PCA for discrete, or MCA. Yeah, I don't know what MCA is, so I cannot answer that. I'm sorry. Any other questions? What to use for the soft clustering error, the per sample average or the weighted log probability for each sample? Yeah,